have an interesting new inequality I want to talk about, or a general proof about an inequality. Now, I'm not going to talk about the proof hardly any, but I'm going to utilize the result of the proof. It's called Young's inequality. And I found out about it at Professor Omar's site. It was really cool how he did it. He used an increasing function, and he used the function's inverse. And he used these values, A and B, as limits of integration. And he appealed, I guess, to the symmetry of the function and its inverse, and showed when the equality condition actually held. It actually holds under this circumstance. And I'm going to relate that to this particular problem. But I'm not going to make any effort to prove it. I encourage you to view that if you want to. It's very cool how he proved it. The proofs I've seen before have been just algebraic in character. He did it totally geometrically based on definite integrals and functions and their inverse. So let's get into this. We're supposed to show that that this value 1953 is less than this right-hand side here. Now, it looks kind of messy, and I would have no, I tried AMGM, and there's probably a way to do it with holders, you know, but I don't understand holders that well. And maybe AMGM, but I couldn't see how to do it. But it turns out this result called Young's inequality is the way to go on this one. I actually designed the problem to work out fairly closely. Now, so the first thing to notice is that your AB, your 1953 is actually equal. 1953 is equal to 63 times 31. Okay, so 63.31, we'll call that. Or 63 times 31. But you'll notice if you just use this result right here, that's going to be less than or equal to. That's going to be less than or equal to 63 raised to the 11 over 16. 11 over 6, excuse me. Now, this is what made this thing kind of appealing to me, at least. The exponent also belongs in the denominator. Okay, so you get this. Okay, now that takes care of this part. Okay, that takes care of this part. Now the next part will be 31 raised to the 11 over 5. Now, so we got it. Now this is just a statement. Literally, it's just I'm just blindly using this result. The proof was cool, but I'm not trying to claim I understand it. I'm just strictly adhering to these conditions right here. And so you got 11 over 5 right here also. Right? Now notice if you invert and multiply, this would be equal to 6 over 11. Okay, this would just be equal to, this would be 6 over 11 in the numerator, you know, you invert and multiply. So you would get 6 times 63 raised to the 11/6 power. And while I'm going real slow here with this writing device I'm using, y'all notice this is pretty close to a nice number. 64 to the 1/6 is actually 2. So you see, that's why this ends up being a pretty sharp inequality. And then right here also you would have 5 times 31 raised to the 11/5. Yeah, I go pretty slow because it's a pain to try to erase on this thing, so I'd rather just go slow and not make any mistakes. So we got 5 times 31 raised to the 11/5. And all of this is going to be over 11, right? Because you have common denominators. When you invert and multiply, this would be 6 over 11 times this. So we have common denominators of 11 in both cases, okay? So you see, this is what we set out to prove. 1953 is less than or equal to all of this, but this algebraically is just equal to that. Okay, I thought that's kind of nice. Now, notice that these are fairly close. Let's go ahead and verify this condition right here. This would be one. This condition of the sum of the reciprocals having to equal 1, that also prevails. If you write this as 1. I'll just write it down. 11 over 6. Okay, plus 1 over 11 over 5. That initial condition must hold for this inequality to hold. Okay, that's it, definitely equal to 1, right? So again, this condition right here. Oh, sorry, folks, I got a little. Hopefully that's readable. I got everything kind of close together here. But 1 over 11 over 6 plus 1 over 11 over 5 does equal to 1. So that condition holds. But now notice right here that this is pretty close. Equality holds if and only if a to the p is equal to b to the q. Well, notice that 60, and I'll just write this down, and you can check it out by comparison. 64, not 63, but 64 raised to the 11/6. That actually equals to 32 raised to the 11/5. Okay, so you see that explains why this ends up being very sharp, and I'm going to write down the decimals here in just a minute. But you see, this is true because 32 to the 1/5 is 2 to the 11th, right? 64 to the 1/6 is 2 to the 11th. So this is true. Notice how close these numbers are. I have 64 right here, 63 right here, 32 right here, 31 right here. So you see, this is just almost the equality condition right here. The equality does hold when this happens. And again, these numbers, 64 to the 11/6, 64 to the 11/6 does equal to 32 to the 11/6. But again, they're very, very close right here. 33 is a little bit below, 63 is a little bit below 64. 31 is a little bit below 32. Okay, so y'all, just if you're curious, this turned out to be very, very close. It's pretty sharp. This is approximately 1953. 1953.41. And again, that can be explained by this truth right down here. This is a dead equality, and that's when equality holds. And again, this number 64 is a little bit more than 63. This number is a little bit more than 31, which makes it easy to believe the sharpness of this inequality. Y'all, I hope that was real. I hope you liked it. And again, I would go to Professor Omar's site and go over this Young's inequality. It's really cool to see it work. I just had to see a concrete example of it in practice. Thank you for viewing.